All right, so we're going to wrap up the shared memory multiprocessors and get into message passing multiprocessors. Running a couple slides behind pace, but we'll be fine. Assuming I remember to actually click the focus back so I can advance the slides. Okay, so we've been looking at spin locks, right? And we've been noting that not perhaps the most efficient thing in the world, but they're fairly simple to express how they would work to provide mutual exclusion. And the ones that we've shown are pretty easy to understand in a system where you have a global broadcast bus where everyone can actually see and snoop at the same time. And I'm just going to claim, and you can go read on your own, if you're looking at a directory-based or other sort of more scalable system, any particular lock location would still have this ordering property. So anything where you're dealing with one lock is just as simple to understand. If you start thinking about ordering among multiple locks on a system that doesn't have global broadcast, things can be a little more interesting. All right, so let's just sort of look at how this would work in practice. Convince ourselves that in fact we are actually getting. Also apologize in advance. I'm probably going to cough throughout. I've been fighting a cold all week. We convince ourselves that we would in fact actually have mutual exclusion, and none of them. You never get the case that more than one of them would have the lock. Okay, so let's imagine a situation where currently port 0 has the lock. It's been acquired. So the value of the lock is set to say 1, it's locked. And so let's say it's been there for some arbitrary period of time. So these can both spin locally, right? So the nice thing about LLSC, right, is that the LL is not by itself an atomic operation. So you can have, this can have been set to 1 at some point. These will read it. Now it's in the shared state across all 3 of these cores, right? The lock variable, the cache line. There's no bus activity. This can sit here spinning, reading the same line that has not changed for as long as is necessary. That part so far local and scalable, right? The weighting is scalable. Now, to release the lock, right, it's going to set the lock variable to unlocked. That's a write. It is going to acquire write permission. It's going to go from the S state to the M state. It is going to invalidate all of the other copies, right? So that act inherently interacts with the with the coherent system. So these spins here don't even have to get to the store conditional. They could just be checking the value. Well, it's still locked. Check the value again, still locked. They don't even have to try to store it. Here, right, we're going to get cache miss has been invalidated. And these are both going to basically proceed in parallel, but we have only one bus. Right? Only one bus. So one of these is going to happen first. There's a point of serialization in the system. Let's just say arbitrarily that C2 gets its cache line miss served before C1. Right? The bus is going to make a completely arbitrary decision about the 2 things presented to it in the same cycle and just order them. So this is going to read the lock variable, right? Say, oh, it's unlocked, right? It's going to then try to swap that with a 1 with the store conditional, right? Meanwhile, core 1 is going to be rereading the lock, right? So it'll get its copy of the 0, right? This store conditional here is going to succeed because the state of this line has not been changed by coherence between these 2 events. So if you're looking at what the coherent state would be at this point here, so when I do the SC, it's going to invalidate just like any other store, right? So this line here is going to have been invalidated by the time that it tries to do this swap. And so it's going to fail, right? So only one of them is going to get the lock. The other one's go back to spinning, right? Now, this is going to have been downgraded back to shared again since something is spinning on it. But again, it's not going to be really a problem because we're basically going to have one unlock that's going to unlock it for everybody. Any questions about, three cores and a spin lock? I know it's not as exciting as 3 men and a baby, but 3 cores and a spin lock is what we're getting this morning. Okay, so what might you want to actually do? Why would you actually need to do any of these sort of synchronizations? Well, imagine you actually want to coordinate on a task, right? So, well, I will note that well-parallelized programs spend as little time as possible talking to each other as they can. Programs that actually do anything interesting tend to involve at least some communication between all of these cores to collaborate on actually producing a common result, right? So let's imagine that one of the things that they have to do at some point, right, is actually, do a reduction. Right? So they're going to do a sum across the entirety of some array. Right? So C sub n is the core's number. A and sum are shared variables, and C sub n is the sorry, I is a private variable. Right? So pretty easy to express. Not a lot going on here. If I've got a whole bunch of cores, then however many cores I have, right, I would like to basically allocate them a chunk of work to do that sum locally, and then add that locally computed value to the total repeatedly. So you can do this in some logarithmic reduction step, standard stuff. Okay, now the first thing that you need to actually do, right, is to actually make sure that every one of your multiple threads has gotten to the same point in the program before you make any assumptions about what's going to happen. So, and then before you reallocate work to do in these series of phases, you need to resynchronize again. So just imagine you've got 10 threads, 10 cores, right? So they're going to basically produce their own local piece of the sum. How you want to sort of, you probably want to do some cache line movement across these so that you don't get any false sharing, but that's fine. Sorry. And so you're basically just going, okay, I got 10 of them. They compute 1/10 of the array. They put it into a sum. Then they are going to reschedule, right, and run on 5 cores. Now, between those two, there's going to have to be some sort of synchronization, right? Each of these phases. We don't know how long this is going to take, right? We can't rely on timing alone to do this. There's not really any scheduling dependence except through memory, right? They have no understanding of whether or not this is done to read the value here, except if they explicitly communicate, right? They're on different cores, right? So we're going to have to set some flags. We're going to have to actually have some understanding of whether the work is actually done. And ideally, right, we'd like all of this work to be done before we try to schedule anything on these next 5 cores. So this pattern of synchronization, right, would be what's known as a barrier. Right? So if you're looking at the standard sets of synchronization primitives that you would want to have, again, you have a mutex, you have a barrier, some other forms out there, Eureka, a little more obscure. It's something used in parallel search. But locks, barriers, and then you get basically counting locks, right? So move down here to semaphores and reader, writer locks. Standard patterns of things. But if you're looking at something like fork join, then what you're seeing at the join is going to be a barrier. So locks tend to be used for fine-grained synchronization on some portion of a resource that might be potentially globally contended. Barriers tend to show up when you parallelize loop nests, right? Often actually between different loop nests, right? So I have a portion of a program, portion of the program has been parallelized. Before we move on to the next portion of the program, we make sure that everyone has done their parallel piece. Again, from a scheduling perspective, right? I don't know if C9 just got like descheduled by the operating system. I don't know how long this is going to take. I have no idea whether for data specific reasons, scheduling specific reasons, this might just take a while, right? Or maybe one of them is really fast, right? Maybe C4 finishes all its work and then would move immediately to the next work to do, and 9 hasn't done it yet. right? So we want to make sure that they all get there at the same point in time. So put a barrier. Barriers are reasonably slow because it is a global synchronization, right? There are lots of ways you can implement them. So you could have a tree of communicating flags, basically, that get everyone to agree in a log structure. So if you have very, very large numbers of cores, like if you have a supercomputer and you have 100,000 cores, right, you're going to use some logarithmic structure to get them to locally agree they've all got to the same point, and then the next group agrees with the next group that they've all gotten to the same point, and so forth. If you have a more modest number, say 10, you might just have a shared counter, and they can all just count how many of them have gotten there. Now, you could imagine that you could do this, again, depending on what synchronization primitives you have that the architecture supports. There may be more or less efficient ways to do it. So I mentioned that fetch and fee, right? There are a number of architectures out there that actually support atomic increment, in which case I don't need a lock around my counter. I just do an atomic increment. Life is good. If I don't have an atomic increment, if all I have is load, lock, and store conditional, right, then I'm basically going to do something where I get a lock, increment the counter, do some logic, unlock. I can do this with mutual exclusion. So I can build this, or even this on top of some of these simpler primitives. Again, not the point of the class, so we're not going to dwell too much on the particular things that you could implement, right? Just to understand that these are common patterns that you would have and how the things would be communicated through memory, right? So again, we don't know anything about the access to this from the atomic sense unless we apply more semantics. That's the thing I really want you to take away. Right? If I have a variable and I just share it in memory, right? Unless I apply some additional actual synchronization primitives around it, you don't really understand how that's going to be viewed across and when it's going to be viewed across multiple different concurrent threads. Right? So use the synchronization libraries that are there. Okay, so here's an example of a standard shared memory sort of machine. So a chip multiprocessor is shared memory on one core. There are some nice things you can do when you're looking at the CMP view of shared memory, in that within this context of a core, I know exactly how many participants there are. So I can design, for instance, some of my coherence structures to understand that there are at most, in this case, 12 possible parties. So I can allocate a fixed number of bits to do various states. But the more interesting thing here, is when you look at these pieces for coherence beyond the chip, right? Then you have to basically say, okay, what sort of protocols are going to work in this setup, where I want to have a notion of shared memory with a hierarchical cluster of 4 of those 12-core chips, and then 8 of those 4-core clusters, right? So I want to have a coherent singular view of my memory across all of this. If you're doing this, you do not have a global broadcast bus, right? There is not some physical wire that a loader store here is going to lock down until everyone has heard that it is doing a load or a store, right? That is not how this works, right? You're going to have dedicated directory systems. It's going to be more complicated. But the interesting thing, well, the implementation is very different. The actual state, the non-transitory states of your coherence protocol may still simply be MESI. This is probably more likely MOSI, MOESI, but the same MSI, MESI, these same ideas of where the stable states in the system are actually going to be basically the same. You still want to get to the same invariance. Doing it is just going to be a much longer walk. Right? Okay. So if you start to have the number of cores that we have today, right, even on one chip, right, you're going to start moving from buses to various flavors of network. There are many, 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 many flavors of on-chip network. So first you go from a bus to a pipeline bus, then you go from a pipeline bus to a ring, then you go to rings, plural. Then at some point, eventually you go to a mesh or a torus, right? Again, all questions of scale. and what your timing requirements are actually going to be. But broadly speaking, shared memory machines do have some scalability limitations, right? So when we talk about that supercomputer with 100,000 cores, it is not a singular shared memory machine. We do not even attempt to do this at scales that are particularly much larger than this, right? A few hundred cores all trying to agree on what value a particular piece of memory has is not something we actually want to eventually bother with. A, for reasons of physical interconnect and communication model scaling, but B, also because of the set of types of problems which are best exploited at different scales. So if I have a problem and it will map to 100,000 cores, right, that tends to have very, very structured forms of parallelism that can be reasonably expressed in other models that are not the standard shared memory model we all grew up in. And so it's less of a challenge to take something that was sort of originally serial, everything shared memory, move it to 2 to 8, way parallelism and call it a day. You're looking at something where, it's been an HPC problem for 60 years and it's never been anything other than a parallel program. And so it's all fine. Okay, let's move to how you go further. Okay. So the key idea in an shared memory multiprocessor, right, is that the cores through some cache system, through an interconnect to memory, we're going to look at a different topology, right? So there's shared memory. Let's push that memory to the other side of that interconnect. All right, so let's give everyone their own private notion of physical memory and then allow them to still talk to each other. We still want to actually have a collaborative computation, right? We still want to be able to think about this as a logically co-designed machine, even if it's actually a bunch of separate components, a little bit of custom interconnect thrown on top. But now we're going to get a situation where this core literally cannot see, reason about, or modify the memory of any other element of this system. Right? We do not have a way to name locations in anyone else's memory. Our physical memory space is disjoint. Right? So there are some nice properties about this, right? I don't need to worry about atomicity issues. If this can't change my values out from under me, right, then some of my logic is much simpler. On the other hand, if I want anyone to know what I did, or I want to know where anyone else is in their computation, we're going to have to do something a little different, right? So basically, if we share data only by explicitly sending and receiving information, then all the ways that we actually have to write our program are going to look different as well, right? In your shared memory machine, I do a series of updates to a shared data structure, and then other people will later read it, right? I don't need to know who has to read it. I don't have to know that in advance, right? So if you're thinking about how I might do that on this sort of machine, you can imagine either when I do my set of updates, I have to tell everyone. That's kind of inefficient. I have to wait until someone asks me if I've changed the data structure. That's an extra round trip, right? I have to have some sort of, coordination in advance about who needs to see what when. Possible, depends on the algorithm, right? Your algorithms will change when you map them to these machines. We'll also find that there's some other pathologies. We're not going to go into it in great detail, but let me briefly note that if your message send and receive are blocking, congratulations on entirely new modes of failure that you can have where you deadlock because you're waiting for a message that will never come. right? Whereas if you have a load or a store, right, I can load a value. The value can be not the value I wanted, but my load will do the load, right? So these have different classes of bugs, right? Again, another way you can look at all of this is today, even at the level of the chip, we are dealing with distributed systems. How explicit we make some of the things that we all know happen in distributed systems, who is responsible for dealing with them, that changes at different scales with different implementations. Okay. So here, implicit message passing, as the name implies, explicit communication. Okay. So when I have explicit send and receive, if I have non-blocking sending and receiving, that's actually kind of awesome, right? So I can basically say, oh, I did some work, let everyone know about it. While I'm doing that, I'm going to go keep doing some more work, right? And does that mean that I need either a little more logic in my communication side of the fence? Probably. Or, even if I have a very simple I/O model, each of these cores can still be, its own actual chip multiprocessor, right? So these are not mutually exclusive. In fact, if you look at these things in practice, right, we will build a message passing model between physical chips, but within a single chip, why wouldn't you still probably have it as shared memory? Right. So there can still be parallelism even within each of the cores in each of these nodes. Okay. If you can express your program in this way, right? From the hardware perspective, this is great because I don't need to figure out whether my coherence protocol works. I can just sort of skip having one. I certainly don't need to figure out how to make it scale. Consistency models are easier, right? In particular, if I have this whole sort of message passing notion, right, I've basically pushed to software all of these things that we just looked at for agreeing on what value something has and when it gets changed, right? So the hardware people are happy. This is a nice way to scale lots and lots of hardware. The programmers and compiler folks are a little more curious about whether or not this is what they want. But for certain particular classes, it's quite natural. Okay. So which of these is going to be possible? Could you have a physically shared memory with a message passing interface? You have a physically partitioned memory with a shared memory interface. Could you have any sort of mix? So it's going to be E, right? All of these are actually possible, right? So I could build something where the physical structure is in fact shared and then enforce this as a programming model, right? So there's a library and a set of interfaces called MPI, the message passing interface. You can compile your program against the message passing interface. And so here's the sort of right way of looking at it. So if you want to look at a situation where even if physically these are not disjoint, unnamability is there, we already have this, right? So this is a very natural model for a multi-threaded program. This is a very natural logical view of a multi process application, right? So if I use the underlying software memory isolation from the perspective of a series of processes using inter-process communication, they might as well be living in this world. They can't name any memory in any other process, et cetera. So whether or not you're running a multi-process workload here, even if the physical backing memory is shared, the spaces, the namespaces are still disjoint, right? Because of the virtualization layer. Right, so you can do that. You can do that in software. Can you pretend that a physically partitioned system that doesn't actually have a hardware-supported, a shared memory system, can be programmed with a shared memory interface? Sure. Not clear that you want to, but you definitely can. Remember, you can emulate anything in software, right? You could emulate an entire supercomputer on your iPad, right? And shortly, before your grandchildren, read your last will and testament, it will have booted, right? You could do it. Not saying you should, right? And all real supercomputers actually use both, right? Use shared memory at the local node, right? It's got a physical shared memory substrate. It will turn out to be more efficient to not craft a message and send it if you're just trying to do an atomic increment to the variable that's in a shared cache, right? So you'll end up writing your program in some sort of hierarchy, but it will almost always be the case where you have small-scale collections of shared memory machines that are collaborating with each other over a message passing interface, right? Okay, so let's give an example of something that works on something more like a message passing model. So this is the Intel Mini integrated core architecture, the MIC. So Knight's Ferry, Knight's Corner, Knight's Landing. Right, so a few generations here of a machine. So it had 72 atoms. Silvermont architecture for the 2015 version. Right now, this is not a standard consumer piece of hardware. Right, you wouldn't have gone out and run Fortnite on this. It's not what it was for. But there were certainly some classes of applications that were kind of interesting. It has a very interesting memory system. So it has 72 cores, but they are not coherent. Right? They're like, nope. It has a mesh that they can communicate on, but that mesh is there for explicit messages through a hardware accelerated message protocol, not there for sharing other memory traffic. Now it actually has even locally a hybrid memory system. So there is one resource of a physically shared memory that all of them can access. It is uncacheable, right? So you don't have to worry about cache coherence on it. So all of their local memories are disjoint spaces, and then there's one common space, because it turned out that if you're building one chip, it does actually turn to be useful to have some shared data that's going through it. And if you want to understand how they share that data, well, that's really up to the software. Right? Now, could you target this? Yes. Did you want to use this for anything other than scientific computing? No. Right? In particular, there's a very large number of fairly weak cores with very wide vector units. Right? So it's looking for very, very specific types of workloads with very, very natural SIMD parallelism. Basically, everyone has been looking at lots of different ways to multiply matrices, sometimes dense, sometimes sparse together. This was one of them. Don't worry, we're still going to get to GPUs in the next lecture after this, so that you can multiply matrices the way people multiply matrices today. Right? Okay. So how's this going to look any different if we want to do that same sort of summing in numbers? It'll look the same, except that you need to actually have explicit sends and receives, right? So again, I don't have to wait and synchronize as to whether or not you have computed your value before I try to read it and execute my next piece of code. I need to actually wait for you to tell me what you computed, because otherwise I have no way of understanding what you did, right? So a slightly different model, but it will look a little bit different, right? So I don't need a global barrier, right? Because I don't need to sort of worry about where all these cores have gotten to. I'm going to be waiting on a blocking receive. Right, so this send may or may not be blocking. You usually have both options, but this is going to be a blocking receive. That's going to provide the same functionality, right, of ordering. So this C4 here, the first thing it's going to do after it computes its own local sum is it's going to block on receiving something from C9. Now, that's going to work if it knows who it's supposed to be getting a message from, or at least it's supposed to be getting a message, right? So again, there are different types of bugs you can get. Right? So you don't want to have something that's sitting there waiting for a message, never going to happen. This needs to know where it is sending its message to. Right? These can be dynamic, but you have to make sure that there's always a matching pair. Right? Otherwise, your machine will hang there forever waiting for something that's never going to come. Reminds me of the Penn State budget. Okay, so same thing's going to happen here. Right, again, I don't need to worry so much about my ordering. I do need to just make sure that for everything that there's a send, that there's a matching receive, or sadness will occur. So for instance, here, if I put an extra receive here, sadness will ensue. Right, you won't just do a load and then realize that nothing was happening. It will sit there waiting forever. Okay. Now, this also means that if you're looking at the ordering that you need here, right, this send here and this send here, I have to have some way of understanding which of these I was actually waiting for. Right, so how you've organized that in terms of different channels or different tagging of your messages to understand who sent it. We're not going to go into that level of detail, but there are some, devils in the details of these protocols for sending and receiving as well. Okay. If you want to look at very, very large scale systems, even on single chips, there's a line of work on what are called scalar operand networks from the turn of the century, which really looked at how you would scale up even single core designs in terms of explicit message passing interfaces, where you could say, do send and receive at the register level. Right? There's some interesting things you can do with that in terms of spreading your program across multiple cores. It never really took off outside of some fairly niche architectures, though. Okay, so same idea, still logarithmic drop. Now, the good news is that these protocols tend to be completely latency insensitive. Right? So think of everything as basically being in some asynchronous FIFO if you're lucky. If you're not lucky, they can get reordered. All right, so if you're building this for a supercomputer, probably you don't want reordering. Makes your life a lot simpler. If these sends and receives are across the internet, everything can be reordered. Right, your packets within each of these messages can be reordered. The messages between each other can be reordered. In particular, if this is a fully scaled system out in the cloud somewhere, and these are separate machines in potentially separate countries, well, it'd be really slow if you have 10 cores in separate countries, but let's not worry about that too much. But there's no reason to believe that, for instance, that these two, or even these three sends are actually all happening in the order you think they are. But a real problem in practice. In general, when you start thinking about message passing, the overhead of performing these explicit communications compared to an individual load and store is high, right? I have to craft a packet, generate a header, even if I'm doing this in a physically shared memory. Right? Even if this is just a bunch of writes into my L3, right? If in order to say I++, right, instead of load plus store, I load a value from one location, I increment it by 1, I craft a header into the message box for some other processor, write a series of values into it, write the I++ value into it, write that I have written it, right? You can see that even if I'm not sending this anywhere, this is more work. And in the more general case where I am actually sending it, over my, Ethernet and InfiniBand, pick your favorite substrate, carrier pigeon, right? It's going to take a while. Right. The other thing you do tend to get here, and let's go back to sort of that notion of, of blocking receive. If you are looking to scale this to internet scale, you also do have to start to acknowledge the fact that these sends might not happen, or they might happen in a corrupted fashion, right? So you do actually need, again, more robust protocols that are potentially actually sending something back in the opposite direction to let it know whether or not anything was ever actually received. So acknowledgements, timeouts, all your standard network fun can start to creep into implementations of this. Now, if you program in this model, you will not have to do all of that usually. That's handled by the libraries you are using. Right? You're doing a send and you're doing a receive in MPI. But the shared memory model tends to assume I've got a small enough machine that my failure probabilities can be ignored. If there is a failure, then I just crash and I rerun my application. Right? You go to MPI and they're looking at scales at which failures are a part of life. Right? In particular, think about if I want to scale something to a 100,000 node supercomputer, right? If the failure probabilities of each of these nodes are independent, they're not, so it's actually worse, but let's ignore that for the moment. If the failures of these nodes are independent, right? Even if the odds of a failure are, say, 1 in a million per day, if I have 100,000 nodes, that 1 in a million per day, 100,000 independent die rolls, like 1 in 10, right? So you need to make these a bit more robust. Okay, so these are slow, but they scale effectively indefinitely. I don't have to worry about cache coherency as an architect. I now have to worry about coherence as a software programmer. But that's okay. If you can understand Rust's borrower, then you can understand this too, right? Only one mutable copy. It's all good. But you also do have a lot more understanding of what is likely to happen, right? So you don't have to worry about false sharing. No surprise. You're not going to try to wonder why everything is slow. You're just going to know because you can measure all the communication that you put into this program. It's not like, why is this program running so much slower as I scale up the number of threads? And then you have to go read some performance counters and realize that everything is a coherence ping pong. Like, no, it'll all be explicit here. You'll know why. Right? But you need to rewrite your algorithms a bit. Right? So again, if you want your program that is very easy to express in a parallel fashion to run in a shared memory machine, you can usually do that. Right? If I want to just do a parallel for loop, I can do that with about 2 lines of modification, right? Hash OMP par4 private I in my code, and then change my makefile to add the OpenMP library to the linker command and call it a day. Great, I now have a parallel program. If I want a message passing program, you got to get out and do the work. Right? You got to actually make the communications and put them into your program. Okay. Similarly, while it's not the best way to do business, because if you have something that you didn't realize was shared, I don't trust that your program works, but it might still work on your cache coherent machine in a way that it obviously would not on a message passing machine as you were sort of building it up as you go, right? Okay. So if you're interested in this, right, you want to look at really high scale stuff. Again, the set of languages here is not going to be universal. It's a really sort of an HPC view of the world. You can do point-to-point message passing, collectives, right? Lots and lots and lots of things that anyone who's working HPC might want. The MPI standard is going to cover it. Excuse me. Okay. So a lot of how you want to approach this is also going to really be a function of what the program is that you're working with. And I'm actually going to split this one step further. I really like to try to differentiate between parallel and concurrent patterns a little bit explicitly, right? So a parallel pattern is something where a bunch of things happen at the same time, right? So, if I express, array C equals array A plus array B, then there is a sort of logical version of this, which is completely sequential, but just very wide, right? All of this happens at the same time. When does it happen? Each of these things happens exactly at the same time as everything else. There's a pretty clear before and after, right? There's an original value of C, there's an original value of A and B, and then after this, A and B have the same value, C has a new one, right? Even if it took lots of writes to do. Concurrency has to do with the fact that there is not a strong ordering, right? So we spend so much time in a sequential model that we're used to fully linearizable temporal relationships, right? Where there is a well-defined ordering between every element of work in our system, right? It's linearized. total order. But as soon as you start getting multiple cores involved, you need to start thinking about a world of partially ordered sets, right? If I have an example, let's say I have a video game, I've got a physics engine, a graphics rendering engine, an audio engine, a network communication engine, right? Those can all be living in their own separate threads. What is the total order of all the events among those? I don't even want to think about that. It's not even something useful to ponder. There are going to be particular points where these communicate with each other, right? My physics engine notices that a collision has occurred and is then going to communicate to these other parts of my system so that you will, in the audio, visual, and global recognition that you just ran into a wall, right? And everyone can come laugh at you. You can all get the right part of the system to do the right thing. But if I'm just sitting there playing the background music in the lobby, right? There's no ordering between that and anything else that is happening in any of these portions of the system, right? Lots of it is just concurrent. And even if you were looking at things that are not so obviously distinct, imagine that I am doing a traversal of an arbitrary graph, right? And I have forked off some different number of threads to parallelize this. What is the relative order that these things are going to hit different nodes in that graph? You're not necessarily all doing them at the same time because it's a graph. Some of these things can converge. There is going to be ordering among when you visited node A and I visited node A, or at least tried to visit node A and realized you'd already visited, et cetera. Right? So there are ordering properties in there, but lots of these parts are not ordered. Right? If I visit node B, you never visit node B. When did I visit node B relative to when you visited node C that I also didn't visit? Right? Ill-defined. All right. Bit of a long walk, but I always do like to say that this is not exactly a synonym for parallel. Parallel and concurrent are different. So it will turn out, we can't prove it, but we have a pretty good intuition that writing correct concurrent programs is just harder than writing sequential programs. Right, again, parallel, not that hard. Par4 is 2 lines, right? Arguably, technically harder, but realistically, it's the same logic, right? Array C equals array A plus array B, I would claim is not actually harder, right? There's a little more work that happens to make the system do it, but the reasoning about it is very simple. But writing programs that are themselves concurrent and then getting them to run on parallel hardware, or even worse, heterogeneous parallel hardware, well, and getting the slope of scaling to be what you want, that is definitely hard. That's not just about expressing your program, that's matching your abstract program to a bunch of finicky pieces of a system that have strong dependencies on finite resources that are not necessarily all statically knowable, right? So if I don't know when your operating system is going to deschedule your thread for no particular reason that I can understand at compile time, I can't understand whether some of these threads that I launched were given the right amount of work to do so that they would all finish at the same time given some number of cores. Do I know exactly how many cores I'm actually going to have? Do I really actually get them? Or is Amazon just billing me for them anyway and pretending that you got about the performance you would have had if I'd actually given you, did I get a core? Did I get 2 threads on one hyperthread? I don't know. Amazon's not going to tell me. If I wanted to know, Amazon will bill me for that too. Actually, Amazon has a billing process for getting performance information about your own programs. Good old Amazon. Okay, so this really is all just coming back to Amdahl's law writ larger with many more factors. So if you've already purged the beginning of class and your entire previous class out of your head, let's just remind ourselves what Amdahl's law was, right? That you have an affected portion, unaffected portion, and your speed up is going to be limited by the portion that's unaffected. Boop. Right. So I'm going to skip over the particular constants here. Amdahl's law was originally formulated for looking at parallel speed up in large-scale IBM processors. Right? So where the original law came from parallelization, right? You can apply this to making a better multiplier, but it came from originally from parallelization. So they were looking at things like if I, wanted to get a speed up of 90 from 100 cores, so I spent at least 100 times as much. I am getting less than 100 times speed up. So already I'm a little bit sad, right? But now, right, how much of my program would have to be parallel? Right, even to hit 90 on 100, I need 99.9% of my program execution time to be parallelizable. Right, so think about a real program. Step one, load some values, do initialization, set up all the different parallel threads, launch them, receive return value, right? Even if everything except the launch and the receive at the end was completely independent, right? You're now in a situation where the ratio between that has to be 999 to 1. There was a amount of work to do, right? If I now in fact have a pattern where do parallel work, agree we've all done parallel work, and we're in a new state, so we can do a new kernel, do new kernel, right? Each of those synchronizations, that's chipping away at this. Actually, it's worse than this. It's worse than this because that synchronization code wasn't even there in your original. So you have overheads relative to your original serial program that have to be overcome. Right? Excuse me. Bloop. Right? So if you're looking at different sorts of parallelizations, right, you can get these range of speed ups. If this was sort of my original on 10, and I go to 100, well, right, I don't have 99.99. I could spend 100 cores and get 10x speed up. And we live in an era where cores are cheap and you can rent them and you don't have to pay the upfront cost of buying them, but still, right, this is fundamentally unsatisfying. Right. So partly this speaks to the scale of programs at which you bother to try to do a parallel execution, right? Also entire classes of algorithms where it's relatively well known that parallelism is hard. So for instance, if I am doing modeling of a discrete finite automata, that's a fairly sequential process. Have state, modify state, move to next state, check how next input modifies state, right? It doesn't parallelize very well. Right? Whereas, as I said, matrix multiplication, it parallelizes very, very nicely, and it is one of the most heavily optimized algorithms in the history of mankind. Right? Now, the good news, if these matrices get bigger, right, things get better. Right? So one of the other things that you have to think about is not just algorithmic scaling, but how does your algorithm scale with respect to parallelism with respect to changes in the input? Right? So here's an easy intuition on why, again, before GPUs were just used for neural networks to tell you that it's afraid of its being shut off and doesn't want to end its life when GPT-4 comes out. Whatever we're actually using our GPUs for today. Think about the graphics problem itself. Right? So think about rendering. So rendering is a pretty parallel process. And it's parallel in terms of the number of pixels you have, right? So the more pixels I have, the more parallel, the more of my total execution is going to be parallelizable, right? Because the problem is naturally expressed at pixel level parallelism for rendering, right? So there are all sorts of problems that actually get really, really, really nice natural algorithmic scaling properties as a function of input size. The bigger my input, right, the larger a fraction of my program is parallelizable. Other things, that's really just not the case, right? So let's say I'm modeling the stock market. The size of the stock market is fixed, right? I can run different algorithms. I can have a different number of cores. I can run for different amounts of time, right? But the temporal aspect is fairly sequential, right? So there are not all these things actually have very good scaling. So broadly speaking, we like to categorize some of these parallel applications and their relationship to their inputs as either having weak scaling or strong scaling, right? So strong scaling means that even for a fixed size of the problem, I can increase the amount of parallelism and get a reasonable curve. Amdahl's law still eventually kills me, right? I'm not going to get linear scaling just because I have strong scaling. Weak scaling is the only way that I am going to get more out of a parallel system is if I'm operating on bigger inputs. So the number of threads that I want to throw at this, the degree to which I'm going to try to parallelize, is only going to go up, not with my number of cores that my system has, but with the size of the input that I'm processing. The other way to look at this is if I have a strong scaling algorithm and I move from an 8-core machine to a 16-core machine, and my input has not changed, I would expect to want to go increase my parallelism from 8 to 16. For weak scaling, I go from an 8-core machine to a 16-core machine. If my input doesn't change, I'm still going to run this with 8 cores if I was running with 8 cores before. There's no reason to believe there is substantial payoff to increasing the degree of parallelism unless, right, I'm also giving you more work to do for the 16 cores than I was giving you for 8. Okay. And yes, I already mentioned all the overheads of synchronization weren't even there in the original part of the program. Why this is running so slow today. Okay. Mostly this just is a reminder that if you want to actually calculate the speed, well, we'll see that in the graph in a second, so I'll get to it. Excuse me. Okay. So if you're looking at some various benchmarks that you might understand whether or not your parallel approach is good or not, how you measure these things. So LINPACK is not the world's most interesting set of applications. The LIN stands for linear algebra. But this is what is used for top 500 supercomputer scaling questions, right? So if we talk about exaflop, we talk about petaflop, right? We're measuring it with respect to dense matrix linear algebra. If you want to use sparse matrix linear algebra, good luck. Its scaling is much worse. It's much harder. But you can still parallelize it. It's just takes more work. Spec rate is job level parallelism. So it's a fairly coarse grained, running lots of independent tasks. Splash 3 is a set of kernels and a few applications which are related to certain things in high performance computing. This is mostly fluid dynamics. Parsec is an interesting one. This is really only for shared memory models. This is designed for. So this really sort of when we started to get to chip multiprocessors. So the original Splash bench, LINPACK is ancient. Sort of makes sense. Linear algebra and supercomputers are old. Right, we've been measuring that for a while. Splash, even though we have a third version of it, the algorithms haven't really changed. These are just updates for sort of modern execution environments. I mean, the original Splash benchmarks are coming out of the 90s. Similar with NAS parallel, right? So these are some, again, these are things still written in Fortran. So we got CMP, we got some new things. The Berkeley dwarves are interesting. They're a collection, not really so much of applications as just design patterns, right? So they're trying to basically classify portions of your execution into one of these 13 different variably parallel-friendly design patterns, and then get intuitions on, so you get to rewrite these as long as it follows the pattern. So the measurements on these are not directly comparable as a benchmark, but they're interesting for exploring. Note that one of these 13 patterns is the not parallel pattern. So they did think of that. Okay. So what would you be trying to do if you wanted to actually parallelize something? You might be trying to parallelize dgem, right? So dense general matrix multiplication. So here's a pretty straightforward setup, your standard triply nested loop. Right? Can you do better? Yes. Right? But ultimately, we're computing the following. Right? This is sort of what a LinPack version of a matrix multiplication would look like. So C is C plus A times B, or C, A, and B are matrices. In particular, matrices of double precision floating point, because in the supercomputing world, that's really what we care about. If you like integers, you're welcome to like integers, but that's not what they're measuring. Okay. Now, if you want to do a very simple version of doing this a bit better than your most naive approach, you get something that looks like this, right? So pragma, how many people know what a pragma is? Got one hand raised. Okay, so a pragma is technically a comment, a hint to a compiler, right? The compiler is free to just do nothing and laugh at you, right? That is legal, right? But you are telling it, I have some additional information for you. And my additional information is that OpenMP can parallelize this for loop, right? So this would be attaching to the outermost loop. This is actually a blocking version of it, so there's already one optimization that's already been done. It's a little cache friendlier than your default naive matrix multiplication. But other than this sort of cache friendliness in the beginning, the rest of this is exactly sort of as you expect it to be. Okay, so how does it work? And again, this is where I'm going to come back to that note. When you do your benchmarking of parallel programs, you always need to normalize, set your 1.0 mark to be the performance of the original serial code with no parallelization overhead. Otherwise, it's not actually a fair comparison. It is actually very common for certain classes of parallelization, right, for the first point on the graph to be below 1. Right? I have my original serial version of the program. I have my parallel version of the program running with one thread. It will probably be slower. There are some overheads, right? So now you can note that one of these curves is particularly sad, right? So if I have a 32 by 32 matrix and I try to parallelize it across 16 cores, yeah, don't quit your day job, right? This is not a good undertaking. The amount of work to do is not sufficient to justify the attempt to get 16 parties to coordinate doing it, right? Right. If you want to think about an analogy for this, imagine that you are out to lunch with 16 people and you try to formulate calculating how much the tip should be as a function of interactions among all 16 people. No, there's not enough work to be done, right? Yes.
But I mean, you're still breaking down the workflow.
You are, right. So if you look at the amount of time spent to do your work, it's small. But if you get the amount of time getting everyone to understand that they have done all of their work, right, is larger than the savings you were getting in the reduction in work. Yeah.
That is what's like talking about like having the unrolling loops or even the right partition. I like seems like stuff.
So a lot of this has to do with if your language did not have an understanding of how parallelism would, could, or should work at the time of its construction, then unless you are changing the language spec, right, then there's nothing for your compiler to know about. The only thing you can have is a hint. It says, I know something, and if you know what to do with this, you could do cool things. But there's no way to express this in the language, right? There's no way in C to say, this for loop is parallelizable, because I mean, we can check the new C23 spec when it comes out, but I'm still going to say that that's mostly just not there, right? So this is a way to bolt things on after and allow different compilers to do different things, to have very loose semantics, right? It's an optimization hint. So this is one of the reasons that they tend to be common. But yeah, ideally, if I were writing a parallel programming language from scratch, in fact, there are lots of languages that are written from scratch to be parallel programming languages, I don't need a pragma. I just tell you par4, and you yell it the same way you yell parkour when you jump across a series of chairs, right? Because we only know that your parkour only works when you scream as you're jumping. Yes. They can, they don't have to. Again, that's the whole point of pragma, right? It's optional. Okay, so you can see different scaling for these different sizes. All right, you move up to a slightly larger one. And again, life is pretty good until it isn't. And for much larger, right, you get pretty good scaling. Now, note, this is 16-way parallelization. None of these get beyond about 13.5. So linear scaling was not in the cards. Right. But, 13.5x speed up is nothing to say no to. Okay. You can also go further, right? So it will often happen that you can think about exploiting the parallelism inherent in a computation at multiple levels, right? If your hardware lets you do it, you're going to want to, right? So SIMD parallelism, a good idea, right? And of course, you can do both, right? I can scale in both SIMD and in my MIMD directions for my parallelism. Right? So you can get curves that are going to go a bit higher. We're going to do an entire lecture on GPUs, but I'll do this just a couple of slide version here to cue it up in the context of these. Oh, look, fidget spinner. Cool. In the context of these highly parallel processing machines. So modern GPUs are multiprocessors. So the right way of looking at it is use the NVIDIA terminology, every SM is a processor, which is a SIMD, well, SIMT processor with a 32 to 64 width. And then your GPU is a collection of these processors of, say, 16 to, better part of 100 of such cores, right? Each core is itself actually not only wide, but also multi-threaded. So think about basically combining SIMD, FGMT, and multi-core levels of parallelism to have throughput-oriented, latency-tolerant machines. Right? Now, it will turn out that they don't have very good latency properties, but as long as you have a sufficiently data parallel form of your computation, the GPUs will scale pretty well. Right? So again, this would be sort of a notion of an SM. This is sort of a logical core, right? So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 cores in your sort of notion of chip multiprocessor land. So each of these cores is itself actually a highly internally data parallel machine. And again, we'll go over the network aspects of this in a bit later. GPUs are everywhere, so we've got these parallel processors in addition to our cores. So if you look at anything you're looking at today that is sort of an APU, where there are both GPU cores and traditional CPU cores on the same machine, then one of the things you have to start thinking about is not just a homogeneous notion of parallelizing your program, but how can I parallelize my program across a collection of CPU and GPU cores? Again, some types of applications, that's fairly natural. Sometimes it is not. So if you want to sort of get a sense of where these have come, this is a log scale, so your discretes are still living quite a bit above your integrated, but the performance of the integrated units has been going up quite a bit. And so if you start to look at how you want to, even at the chip level, optimize your parallel programs, there is something to be said there about thinking about that. Okay, let me check the time. We're good. So one of the nice things about the MPI model, given that it doesn't really specify what the interconnect is, is that even if I didn't actually co-design all of my machines together, as I would with a supercomputer, I could still pretend. Right. So if I want to do parallel computing on the cloud, I can. There's an even older version of cloud computing. It used to be called grid computing. If you're of a certain age, you've probably never heard of grid computing. But if you see anything talk about grid computing, they're just an old person talking about cloud computing, right? So there are some challenges in using large collections of sort of off-the-shelf independent computers and pretending that they are a larger scale computation platform. So again, if you worry about load balancing and you worry about heterogeneity and you worry about different levels of communication, reliability, and bandwidth, this is that writ large. There are a bunch of things that are not optimized for this. Right, so everyone is wasting a bunch of resources doing all of the things that they would do if they were their own independent computer. They don't actually necessarily have to if the only thing you were going to use them for was getting these things to collaborate. That said, this is really a financial reason to build your machines this way rather than a technical one, right? So if I want to look at the right way to build a 100,000 node supercomputer, right? It's not going to be the same way to build a 100,000 nodes in my data center. And the 100,000 nodes in my data center are going to be a heck of a lot cheaper. But the good news is 100,000 nodes in my data center can run a lot more things usefully than my 100,000 node supercomputer. Most programs find it very difficult to use much of a 100,000 node supercomputer, but 4 million different people, all running their same terrible e-commerce site can very easily use my 100,000 nodes of my commodity products. Okay. So just in terms of some nomenclature, I'm going to show you a top 500. So top 500 ranks the performance, or has some other metrics as well. There's now a green 500 of the sort of best supercomputers in existence. These are ranked in terms of their LinPack performance, which, as we said, was weakly scaling. Excuse me. But this is where you're sort of looking at different groups competing for, teraflop, exaflop, petaflop benchmarks, and so forth. So most of these aren't around anymore on the top 500 list, but if you go back far enough, there were some uniprocessors. We're looking at the most powerful computer in the world in the 1970s was, an old Cray vector machine. Right, so very parallel, but single processor, right? SMPs, MPPs, constellations, clusters, right? They have gotten almost entirely, basically, you just stay basically down to these two classes if you look today. But we'll show you, right? So if you look, want a little more color in your graph, right? So if you look from, say, the early 90s through the mid-late 2000s, don't worry, we'll switch to the modern version in just a bit, but this is zoomed in so you can actually see it. Yes. This is the fraction of so there are always 500 in the top 500, right? And this is basically the proportion of the top 500 that belong to one of these classes of building an HPC type machine. No, these are not ordered. This is the number of machines of a class. So this is saying that in 1993, a bunch of the top 500 machines were, like Cray-style vector machines still, right? And then those dropped off the list, and then there was one, and then there were none, right? No, it's how much of the y-axis. This is just proportion, right? So we can see the change in how we have built HPC machines, right? So by 2009, it's basically MPPs, clusters, and a little bit of constellations. And if you go to this, right? So now you look at the same sort of thing zoomed all the way out, right? Now it's almost entirely clusters and a little bit of MPPs, right? So you can sort of see the breakdown there. You can also look at what these machines are doing. These are heterogeneous machines with acceleration. So this is a look at the accelerators that are in use in these machines. So you can look at a breakdown on what fraction of these machines were using different classes of GPUs to get their position on the top 500 list. So what do you want to take away from this? Take away the following. There's a Xeon Phi. Got something that isn't a GPU. Yay. Real large-scale computing in HPC space has a hierarchy of ways that you are trying to parallelize your program for reasons that are both economic and technical, right? So these are very good parallelization machines, but they are not complete computers. So you're going to have a high-performance core, multi-core, paired with an accelerator device. There's going to be some sharing within the cores on that machine, sharing between the cores and the GPU on that machine, sharing among the machines locally within the multi-socket local network that are probably all at least a mostly shared memory model, which are then communicating in a message passing interface at the next level up. But they probably actually also want to understand that some of them are in a rack where the communication loss factor is basically 0 and the latencies are still in tens of nanoseconds if you're using enough money on your InfiniBand. And some of them are on the other side of the warehouse size building, and your mileage is going to vary a bit. So if you really want to make things run really fast, you need to know a lot of things. But we just as of last year finally hit exaflops, right? We have built single systems, right, that can actually hit 10 to the 18th floating point operations per second on LinPack, right? So you can look at a few things that got there slightly earlier, right? So you can get a an exa not flop, an exa op per second calculation from Oak Ridge is a little bit earlier. That was in 2020 in March. There's a Japanese computer that hit on not LinPack, hit exaflop levels and also in 2020, but we finally hit exaflops in 2022. The other thing you can do when you stare at this sometimes is look at the fact that some of the winners of the old top 500 and then compare them to your cell phone. It's always a sort of a fun exercise. Where does your cell phone, at what year would your cell phone be topping the supercomputer list? Right, but what was that? Oh, we're out of time, so I gotta cut in the interest of time. But if you're looking at, well, they're definitely hitting gigaflops. Whether they're hitting teraflops is not usually the case unless because you need some interesting graphics processing to happen there. But yeah.